Alright, so today we're going to start looking at the acceleration due to gravity. In order to talk about that topic, I'd like to start with someone who's somewhat of a hero to physicists, and that is Galileo. So Galileo had the radical idea that what you do first is to gather evidence, and then based on that evidence, you decide what the truth is. Prior to that, people had all kinds of crazy ways to try to decide what the truth was. So one of the things Galileo was interested in is gravity. I mean, what is this thing that causes things to fall down? So he might have said, okay, well, here's something that's going to fall. Great, right? Except that happened so fast, he couldn't figure out what was going on in that short period of time. So I like to say that what he did was something everyone should do, which is if you can't do the experiment you want to do the experiment you can do. And so the experiment he thought of to do, reasoning it's probably the same sort of motion. If you let a ball roll down a ramp, you can have that ball rolling down the ramp very slowly, like this. And so if you could measure that time accurately, and then say measure another time halfway through, with the ball flowing only half the distance, then you should be able to determine something about gravity. What's the essence of the gravity? What is the mathematical relationships in gravity? So, pun intended, Galileo got the ball rolling for physics. And it turns out, it's reported that he did so many of these experiments that eventually what he did was to use his own pulse as his timer. And so, gathering much data with his pulse and other methods as well, he was able to find a relationship between the position and the time it takes for a ball to roll to the end of a ramp. So, what we're going to do next, in the next section, is to use our modern day tools to do a similar experiment. We're going to use a cell phone. So to get started, we'll look at the inside of your cell phone's brain. There's an XYZ sensor for acceleration in XYZ direction. So for example, right now the cell phone knows that it's looking down. If I lift it up and look at the face, it might think, well, you're about ready to dial a number. And then when you put it to your ear, the cell phone might say, well, now it's time for you to talk. Or for example, you might just like this and walk along with it like that. And you might get some signals that would be similar to what a Fitbit, for example, would do to count your steps and to know how far you've gone. So if you take a look at this data.
Let's now examine the collected data in more detail. There is a lot going on here. First, how do these accelerometers in phones and Fitbits work? I'd like to use a diving board analogy. Here we have a diving board with no mass on the end of it. It is neither pushed up nor pulled down. When I place a mass at the end of the board, it bends. A similar process is taking place in the accelerometer of a phone when the board feels the effect of gravity. In the sensor, the board is made of a piezoelectric material. That creates a voltage in proportion to the strain on the board. Of course, the sensor is minuscule compared to a real diving board. This represents our initial condition. The phone is face down on the tabletop. The yellow trace shown, constant at 9.8, negative 9.8, says that the phone is pointed straight down. You can't see the axes on the graph. There are also two other sensors that point in a horizontal direction. Those sensors register 0, since gravity is not in effect in the horizontal direction. The red and blue signals lay on top of each other, forming a purple line at the top, at a value of 0. In this diagram, we are looking from below the table, the yellow direction pointing straight at us. The red and blue sensors are for accelerations along the surface of the table, which is 0 at this time. The situation when free of the influence of gravity is illustrated by rotating the diving board up by 90 degrees. When the board is perfectly vertical, it does not bend, and the sensor reads a value of 0. Suppose that the base of the diving tower, now laying flat, is pushed. I suspect it is quite intuitive that the mass will delay the movement at the end of the board, thus bending it. Likewise, the tower could be pulled, and the board would bend in the opposite direction. The sensor output would be of the opposite sign. So the accelerometers can detect a change in the motion, an acceleration, as well as gravity. Once I pick up the phone, all three of the sensors spring to life. You see the major accelerations of the phone that my arm and hand have made, but also a lot of jitter in the small motions of the hand. These accelerometers are exquisitely sensitive. At the same time, each sensor will also register the changing angle of the phone. This diagram shows that a red or blue sensor can also be aligned perfectly with the down direction. In the first placement of the phone in front of my face, as though I was reading a message, the yellow signal turns positive, but only by about half, since it is not pointing straight up. The red signal now shows a contribution based on the angle of the phone. The red sensor now recognizes the acceleration due to gravity. The blue signal records the small jitters of my hand, but for the most part is at 0. The blue sensor direction is mostly horizontal. Then when I lift the phone to my ear, a new arrangement occurs, where the blue sensor is at an angle to gravity, along with red, but the yellow direction, pointing straight out of the glass, is mostly horizontal. Finally, when walking with the phone in my hand, all three sensors show the pulse of the pace, with red and blue oscillating their orientation with respect to gravity. They show that the phone is mostly upside down and swinging back and forth.
Okay, so now what we'd like to do is actually use the phone as Galileo would have liked to use the phone and just drop it and see what kind of signals we can see when we do that. So I'm going to climb up here and drop it first from 100 inches.
This was the moment we've all been waiting for, dropping the phone to see what happens, similar in a way to Galileo rolling a ball down a ramp. I can take the image on the projector directly from the computer screen to provide this high-quality view of the event. Once again, there is a lot happening. Start from the left where I am holding the phone as still and as level as possible as I prepare to drop it. These signals are just a shaky version of the phone sitting face down on the table. Notice also that after the drop, on the right side, the signals look exactly like the phone sitting on the table, but it is face down and stationary on the pillow instead. At the moment the phone is released, the measured effect of gravity becomes 0. This diagram explains the situation. Imagine that suddenly the ground holding up the tower, the board, and the mass is removed. The tower and the board fall, and the mass also falls, but independently, so that it can no longer bend the board. The sensor reads 0. Also, the two horizontal signals, red and blue, lie completely flat, very near 0. When the phone is falling, there is no way to reference any acceleration. We and other physicists call this state a free fall. We'll discuss the curious case of the bending yellow line later, but first note that it is easy to tell the time it took for the phone to fall 100 inches. Using the red line, for example, by measuring the time that the sensor reads a flat 0 to the time it again responds as it collides with the pillow, we can know that the phone fell for 0.68 seconds. I'll show this in more detail later. Galileo would have certainly been thrilled to see this. 3 more drops were done to try and find a relationship between distance fallen and time. Here is a high-resolution view of the result of all 4 drops. To understand this, we can start by looking for the times that the phone was resting on the pillow. Just before those areas, the drop occurred. Since the total time to perform the experiment was quite long, it is only barely observable that the time to fall became shorter as the drop height decreased. To be more precise, we must analyze the data. I turn now to data from another identical experiment. I too have performed these trials many times. Here I offer an analysis of the acceleration data with the hope of determining the acceleration due to gravity. I will use LibreOffice Calc, a free program that offers almost all the functionality of Microsoft Excel. We'll start with another view of the 100-inch drop. On the left in column A is the time in milliseconds. Note that the value increases by about 20 at each sample. This was the fastest practical speed that also supports showing the data on the screen. The next 3 columns are the XYZ sensor data, using the same colors as you have seen before. We want to measure the time it took to fall 100 inches. To do that, the graph tells me to go looking at a time just after 8200 milliseconds. I've captured that data and brought it closer to the top so we can look at it. As you can see, it is quite easy to determine when the sensor output becomes very close to 0 and changes very little. I read from the columns that the fall starts at 8240 and ends at 8920 for a total of 680 milliseconds. Let's be conservative and claim 2 significant figures for a time of 0.68 seconds. I'll scan down the tabs at each shorter distance to see the times of fall. 75 inches, 0.60 seconds. 50 inches, 0.46 seconds. 25 inches, 0.33 seconds. 12.5 inches, 0.21 seconds. Don't be deceived by the graphs. They are rescaled and only appear to be about the same time at all drop distances. Just to emphasize this point, I've plotted 3 drops on the same axis in this tab. According to the way we have done the experiment, the distance fallen is the independent variable. That is the variation that we controlled. And the time taken to cover that distance is the dependent variable, the outcome of the experiment. As such, we should plot time on the y-axis and distance on the x-axis, as shown in the graph. And by now it is high time that we switch away from inches to meters as shown in the columns at the top left. We just multiply inches by 0.0254 to get meters. It also makes perfect sense to include a 0 point in the data. It is undeniably true that it takes 0 time to fall 0 meters. This might remind you of a square root curve. The trend line confirms this, showing a power of x equal to 0.56, close to the 1/2 that we expect. But in physics, it is entirely natural to consider time to be the independent variable. Time marches forward and stuff happens. It is not completely prohibited to change our perspective and plot time on the x-axis and distance on the y-axis. Now the curve looks parabolic. Let's fit a polynomial trend line of order 2 to the data, setting to show the equation and the r-squared value on the plot. This is a bit statistical, but for now I'll just say that the closer r-squared is to 1, the better the trendline equation represents the data. In this case, it represents the distance fallen as a function of time very well. You will see why as you study physics further, but the coefficient of the x squared term, doubled, is the measurement of the acceleration due to gravity. We get 9.46, which will round off to 9.5 meters per second squared. Way back when we first started looking at the cell phone signals, we found that the yellow sensor, with the phone laying face down on the table, registered a value of negative 9.8. That is because the accelerometer is calibrated to give the expected value for the acceleration due to gravity. We usually just quote the value as 9.8 meters per second squared, realizing that the sign, positive or negative, depends on whether the phone is face down or laying on its back. Our measured value of 9.5 meters per second squared shows an error of 3%. Not bad. But might there be an explanation for this error? I'll look into this and the strange case of the curving yellow signal during free fall in the next section. The background image for this section has captured a moment when the cell phone is falling. You can see the blur right here. Note on the screen that what was an acceleration due to gravity became 0 when the phone is released. What is really happening during the fall? Everyone alive during Galileo's time was well aware of the power of moving air. They observed that ships can sail at sea and houses and people can be blown away by the strong wind. Galileo was also aware that air can have an effect on measurements of gravity. In this way also, his use of a ramp was very smart. Not only did it slow the motion down to measurable proportions, it minimized the effect of air resistance, which he knew would certainly become important for quickly falling masses. Note that the acceleration due to gravity that was measured with the falling cell phone, 9.5 meters per second squared, was just a bit less than the accepted value. This would be expected if the air slowed down the phone. Is there any evidence that air resistance is the reason for the acceleration was less than expected? I did some experiments to try to answer this question and to find out why the yellow signal changed during freefall. Here in this spreadsheet is a record of 4 drops of the phone, face down, as was done in the lecture hall. In each drop, the yellow accelerometer shows a change as the phone falls. But if the cell phone is actually in free fall, we expect the accelerometer reading to be 0 during the entire fall. Could the yellow signal be a record of air resistance? To try to confirm this hypothesis, I dropped the phone from a vertical position, that is, straight up and down, so that the red sensor is aligned with gravity as in this spreadsheet. In this orientation, the phone is much more aerodynamic, slipping through the air without interacting very much. You can see small aberrations in the signal in 2 of the drops. This variation is different than that of the yellow signal. Variation only shows up just before pillow contact and is not consistent. Yet it was possible to see a case where all the sensor readings conformed to a free fall expectation. The precise position of the phone as it falls is not easily controlled. I'll pick that middle drop that seems so perfect to contrast with the face down drop, as in this spreadsheet. The phone slips out of my hand around here and falls freely until here. For the most part, the yellow and red signals are identical, so you don't see much of yellow. This is free fall. There is no reference or point of contact, so the sensors all read 0. In contrast, this yellow sensor output is not 0 and changes in a way that would be expected for air resistance. If we imagine the phone could remain aligned face down as it falls from a very high height for a very long time, the air will eventually act more like the top of the table. Not in the sense of colliding with the table and breaking the phone, but in the sense that the fast-moving air, from the phone's perspective, becomes firm, supporting the phone and limiting it to a constant speed. When that so-called terminal velocity is reached, the yellow accelerometer reading would again be negative 9.8. What we see is the beginnings of this firming of the air. At this point, many viewers will be asking, what about force? In fact, calling the sensor in the phone an accelerometer is a misnomer. It doesn't really represent acceleration of the phone, as we have seen, because the phone was not accelerating at all when placed on the table. Since the phone's mass does not change, the accelerometers give a signal that is proportional to the force on the phone, but only when referenced by some opposing force. For our phone at terminal velocity, the Earth applies a force down, and the air supplies a force up. When the two balance, the speed becomes constant. Note also that when the phone is resting on a table, the same situation prevails. The speed is constant, but at 0 meters per second. When falling face down, the cell phone accelerometer measures the force of air resistance. We used a cell phone to measure the acceleration due to gravity and witness air resistance. What did Galileo learn from his rolling ball experiments? He didn't measure gravity's acceleration as we were able to do, but confirmed something more fundamental, that the acceleration due to gravity is constant, and that because of that, the distance covered by an object moving with a constant acceleration increases as the square of the time of the motion. For most people, simply being told about physics is not enough. It takes time, practice, and deep thought to really see how physics explains our experiences with the world. You'll get plenty of opportunity to understand and practice, both in lecture and lab, throughout the semester.